Welcome to this interactive physics simulation exploring the motion of a simple pendulum. Today, we will break down the precise relationship between position, velocity, and acceleration. As the pendulum bob swings back and forth, its mechanical energy continuously shifts between gravitational potential energy and kinetic energy. By tracking these changes visually with color-coded vectors, we can easily see exactly how the forces of gravity and string tension dictate the bob's speed and path at every single moment of its swing. This visualization makes it easy to understand how energy conservation forces the pendulum to repeat its path perfectly cycle after cycle without losing momentum, assuming a frictionless environment. Watch closely as the energy bar on the right side shifts from orange to blue, showing this flawless transfer of energy in real time as the motion plays out. Let us start by looking at the velocity vector, which we will label as v. When we set the pendulum length to 19.4 meters and the maximum angle theta to 60 degrees, we see a prominent green arrow pointing tangent to the circular path. This vector represents the instantaneous speed and direction of the bob. The v-vector reaches its absolute maximum length at the lowest point of the swing, where gravitational potential energy has completely converted into kinetic energy. Conversely, as the bob climbs higher toward its peak amplitude, the v-vector shrinks smaller and smaller, demonstrating how the object slows down due to the opposing pull of gravity. Understanding this velocity vector is crucial because its magnitude directly determines the amount of kinetic energy present in the system, as well as the strength of the centripetal force keeping it on track. Next, we look at the acceleration components when the bob is near the bottom of its path, with the length set to 20 meters. The total acceleration is split into two vectors. The radial acceleration, labeled as a, points straight up the string toward the pivot, keeping the bob moving in a circle. The tangential acceleration, labeled as IT, points along the curve, showing how much the bob is speeding up or slowing down as it moves toward or away from the center. Near the very bottom, the radial acceleration IR becomes very strong because the velocity is at its highest, requiring a larger force to change the bob's direction along the arc. Meanwhile, the tangential acceleration IT shrinks to zero at the exact center point because there is no net horizontal force slowing it down or speeding it up at that precise split second. Finally, let us look at what happens at the very peak of the swing, where the pendulum reaches its maximum angle. At this exact split second, the bob momentarily stops moving, meaning its velocity drops to zero. Because the velocity is zero, the radial acceleration IR also drops completely to zero since no turning force is needed when there is no speed. The entire acceleration is now purely tangential, labeled as IT, creating the maximum restoring force that pulls the bob right back down toward the center to start the cycle again. This maximum tangential acceleration aligns perfectly with the peak of gravitational potential energy, setting up the ideal conditions for the bob to slide back down the arc, rapidly building its velocity vector, v, once more as it repeats this beautiful, continuous harmonic motion.